Hello. Today's topic is about differential equation. What is a differential equation and what are the application of it in the field of engineering? But before we'll start, at the end of this presentation, the student should be able to classify the type, the order, the degree, and linearity of a given differential equation. Let's start with the definition of differential equation. So it says here that equations containing the derivatives of one or more unknown functions with respect to one or more independent variables are called differential equations. Differential equation is just simply the equation of derivatives. So regardless, whatever would be the order of the derivatives and the degree of those derivatives. Differential equation plays a vital role in the field of engineering. So since this is the one or among the foundational mathematics in the field of engineering. In engineering, so usually we are representing every problems that we encounter in the field into its equivalent mathematical model. So once we were able to formulate the mathematical model based from the encountered problem or based from what we want to do or to resolve something in the field of engineering, then we'll be able to analyze more how a certain system performs and how are we going to improve it and how are we going to resolve if there will be some problem that we might encounter during or the design process or even after the design process. In various engineering fields, so in particular, let's say for civil engineering, so differential equations is usually used, for example, on the rollers of a building to respond properly during an earthquake. So the amount of time or the changes on those rollers with respect to time so would affect what would be the response of the building whenever there is an earthquake that would happen. In the field of aeronautical engineering, so usually the differential equation is used in computing the wind effect in terms of the wings of an aircraft, so which is used in determining the safety of the aircraft in flying. Likewise, so in electrical engineering, its electric circuits could be represented into its equivalent differential equation. So as such, various parameters for electric circuits could be computed so using the equivalent differential equations. So similarly in electronics engineering, so differential equations could be related to signal processing of images, comparing one images to other images, so would be in a way a part of differential equations. Mechanical systems, particularly the gearing system of a mechanical device, so follows the principles of differential equation. So in such a way that the stability of the gear system is used, okay, to determine the maximum load that can be handled by a certain system. And lastly, in the industrial engineering, particularly in a production line, if we want to maximize the production output, so while minimizing the cost, part of it would be a principle of differential equations. So in the field of engineering, so those are the applications of differential equations. However, outside the field of engineering, so we can use as well the principles of differential equation. So such as the spread of a virus can be predicted once we were able to employ the differential equation equivalent to the spread of the virus. So in such a way that, let's say, for a certain period of time, these are the amount of people that were affected by the virus. Once we were able to develop the mathematical model equivalent to that spread, so we'll be able to determine so how many people will be infected over a certain period of time. In forensic, okay, so forensic experts is using the differential equation as well in solving crimes. So let's say if there is a murder that was committed by getting the body temperature of the victim, so the forensic expert could use the principles of differential equation in computing the amount of time elapsed. So since the death occurs or since the murder was committed, okay, so that is through the use of the Newton's law of cooling, such parameters. Okay, so the time that the victim was murdered so can be determined so through differential equations. So in banking, so we are using as well differential equation in computing the interest rate of the amount of money that was deposited over a certain period of time. So as long as there is a change on a certain amount over a period of time, so that can be resolved using differential equation, because mostly differential equations correspond to a certain parameter that changes over a period of time. So those are the some applications. So why differential equations is practically very important, or mathematics, or why it is a foundational mathematics where the professional courses so usually derive their principles, okay, or the mathematics behind the systems on how they work. That is the differential equations. Okay, so those are the applications of differential equations. So let's now proceed with how do we distinguish a differential equation, because there are different ways on how do we classify a differential equations. So let's start with, or these are the different classifications. So we have the type, and then we have the order, the degree, as well as the linearity. So we can classify a differential equation according to its type, according to its order, according to its degree, and according to its linearity. So let's start with according to type. So there are two types of differential equations: the ordinary differential equation as well as the partial differential equations. In our course for this semester, so we will only be mostly dealing, or we will only be dealing with ordinary differential equations. And partial differential equation is usually tackled on a multivariable calculus. For differential equations, we will be focusing on differential or ordinary differential equations. So how do we differentiate ODE from PDE? So differential equations, so containing only ordinary derivatives of one or more unknown functions with respect to a single independent variable. So regardless how many dependent variable that we have, but as long as we have one independent variable, so that is considered as an ordinary differential equations. So for partial differential equations, so those are equations involving partial derivatives of one or more unknown function of two or more independent variables. So the key term here is not only about the partial derivatives, but the number of independent variables. So if there are two or more independent variables, so that is considered partial differential equations. and the other one is single independent variable, so that is considered ordinary differential equations. So as I've mentioned, so we will be covering only ordinary differential equation for this given semester. So let's have an example on what is the difference between an ordinary differential equations and partial differential equation. So on the first one, we have dy over dx plus 5y is equals to e raised to x. We have the dependent variable y, and then we have the independent variable x. So since there's only one independent variable, so which is the ex, this one. So since there's only one independent variable, which is x, so therefore that is considered as ordinary differential equation. So likewise, the second equations here. So we have the second derivative of y, so with respect to x squared, minus dy over dx plus 6y is equals to 0. Again, so our dependent variables here are y, and then our independent variable would be x. So in this case, so this is still considered as partial or ordinary differential equation. So lastly, so we have the partial differential equations. So let's say in this case, so we have the dependent variable and the independent variable. In this case, that will have an x squared and a y squared, or the second derivative for x and y. So the partial derivative there would be considered as a partial differential equation. So aside from it is a partial differential equation or partial derivative, it also contains two variables, so which are the x and y. So that is how we classify ordinary differential equation from the partial differential equations. So let's proceed with the order of the differential equations. So the order of differential equation is the order of the highest derivative in the equation. So since differential equation is an equation of derivatives, so the order so corresponds to the highest derivative within the given equation. So for example, if I would have dy over dx plus 5y is equals to e raised to x, so the highest derivative here is the first derivative, so which is dy with respect to x. Therefore, that is considered as a first order differential equation. While the second example that we have here, so it says that the second derivative of y, so with respect to x, minus the first derivative of y with respect to x plus 6y is equals to 0. So there are two derivatives that are involved here, the dy over dx, as well as the second derivative of y with respect to x. However, the higher derivative here would be the second derivative. So therefore, it is considered as a second order differential equation. And lastly, we have the third equation, the second derivative of y with respect to x, plus 5, the first derivative of y with respect to x raised to 3, minus 4y is equals to e raised to x. So as you can see here, in determining the order, we are only looking at the derivative. So we are not looking at the exponent of the derivative, but we are only looking at the derivative. So in this case, even though that dy over dx is raised to 3, so that doesn't mean that we can distribute 3 in such a way that it will become the third derivative of y with respect to x. No. The derivative involves only a first derivative of y with respect to x. regardless of the exponent there. So therefore, on this given equation, differential equation, the highest derivative is still second derivative. So therefore, that is considered as a second order differential equation. So that is on how do we classify the order of a differential equations. So we are just simply looking at the highest derivative. Okay? So the highest derivative is the order of the differential equation. But what is the importance of knowing the order of the differential equation? So why do we know that it should be a first order or a second order differential equations? So in finding the solution of a differential equation, there are different methods that we can use. So we could use, let's say, the separable equation, say the methods of exact equation. So we could also use the variation of parameters as the method in finding the solution of differential equation. But those methods could only be used depending on what would be the order of the differential equation. So in our syllabus, for the first or for the preliminary period, so we will be covering first order differential equations. So all of the different methods that will be taught here so pertains to first order differential equations. So those methods are only applicable for first order differential equations. Anything higher or two, second order and higher, so those are classified as higher order differential equations. The methods to be used in solving higher order differential equations will be different. Okay, so for example, the variation of parameters is used in determining the solution of a higher order differential equation. So likewise, Laplace transformation could be used as well in determining the solution of a differential equation. So that is the idea why do we need to know what is the order of a differential equation, because not all methods are applicable on a particular differential equation. It usually depends on the order of the differential equation. So let's proceed with the second classification, which is the degree. So it says here that the degree of the differential equation is the same as the exponent of the highest order derivative in the given equation after the equation has been rationalized or cleared of fractions with respect to the derivatives. So in determining the degree, we are always looking at the exponent of the highest derivative. Okay, so regardless, whatever would be the exponent of other derivatives, our main concern will always be the highest derivative. What is the exponent of the highest derivative? So from there, we'll be able to determine the degree of the differential equation. So let's have the first example again. So dy over dx plus 5y is equals to e raised to x. The highest derivative here, so there's no confusion here since there's only one derivative, and that is the dy all over dx. And from here, the exponent of dy over dx, so since there's no any numerical value as the exponent of it, so obviously the degree of that will be 1. So therefore, that would be a first degree differential equation. On the second example, so there are two derivatives that are involved. The second derivative of y with respect to x and the first derivative of y with respect to x. So as you can see here, 3, it could be a 3. However, the 3 is an exponent of dy over dx, and dy over dx is not the higher derivative. So the second derivative of y with respect to x would still be considered as the order. So therefore, the exponent of the second order or the second degree differential equation here is still 1. So therefore, the second equation is still classified as first degree. And then lastly, so we have the second derivative of y with respect to x, and then that would be equal to the first derivative of y with respect to x. Although from here, so we can see that the higher derivative here is second derivative. And looking at the given equation, the exponent of the second derivative is 1. However, based from the definition in finding the degree of the differential equation, it says there that the differential equation should be rationalized and it should be free from irrational exponents. And in here, so we could see that there is a rational exponent for the dy over dx. As such, so we need, okay, so what we are going to do is we need to remove the rational exponents. And on how to do that, so I'm going to raise the entire equation by 3 in such a way that it will become the second derivative of y, so with respect to x, and then that would be raised to 3 and then equal to dy over dx. And then from there, so removing the rational exponents of 1/3 into simply 1. And from here, so we can see that the higher derivative, so which is the second derivative of y with respect to x, this time has an exponent which is 3. So therefore, making the degree of the differential equation equivalent to third degree. So those are, or that is how we classify the degree of the differential equation. So let's proceed on the last classification of the differential equation. So we could classify a differential equation according to its linearity. So whether the differential equation is linear or not. An ordinary differential equation of order n is called linear. Okay, so if it may be written on this given form, a sub n of x, the nth derivative of y with respect to x, until it will be equal to a g of x. So whether a differential equation would be considered linear or non-linear, so there are 3 properties to determine the linearity of a linear ordinary differential equations. So the first criterion is that dependent variable y and all its derivatives, y prime, y double prime, or the second derivative after nth derivative, are all of the first degree. So in short, if a differential equation would have a degree of 2 and above, that is already considered as non-linear differential equations, because linear differential equations only involves a power which is equivalent to 1. Okay, so for every given term. The second criterion is that no transcendental functions of the dependent variable is present in any term of the differential equation. So no transcendental function of the dependent variable. So take note here that we are only talking about dependent variable. So we are not talking about independent variables. So our main focus in determining the linearity of a differential equation will only be we will only be looking at the dependent variable. In this case, that would be y. It depends, okay? So which would be the dependent variable? So when we are referring to transcendental functions, so remember the transcendental functions are example of which would be trigonometric functions. So let's say our dependent variable is y. As long as we have seen there, let's say sine y or a cosine y or a tangent y squared. So wherein y is a dependent variable and trigo function is a transcendental function. So therefore, that is a nonlinear differential equation. If let's say I'll have an x, then it's a sine x. Okay, example, a sine x. So if the dependent variable is y, and then it appears on the differential equation, so it has a sine x, that is still considered as linear because y there or x there is an independent variable. But if it already involves, let's say, e raised to y, wherein y is a dependent variable, therefore, that is already considered as a transcendental function of the dependent variable and thus making the differential equation as nonlinear differential equation. And lastly, the third criterion is that no product of the dependent variable y and or any of its derivatives exists. So what do we mean by that? So if I would have a variable y and then I would have a first derivative of the dependent variable, let's say y prime. So y prime is already considered as non-linear. Okay, so since there's already a product of the dependent variable and its derivative. So that is the third criterion for the properties of linear ordinary differential equations. So as a summary, how do we look at it? So first, we are only looking at the dependent variable. First thing first is the power of all the derivatives of the dependent variable should always be equal to 1. Anything other than that, that is considered nonlinear. Likewise, the equation should not involve a transcendental function for the dependent variable. So we could not have a sine y, we could not have a cosine y, we could not have an e raised to y because that is considered as a nonlinear ordinary differential equation. And lastly, there should be no product of the dependent variable y and its derivatives. So once there is an existing product of the dependent variable y and its derivative, that is considered as nonlinear ordinary differential equations. So those are the different classifications of ordinary differential equations. Their classification would be in terms of type, ordinary differential equations and partial differential equations according to order. So wherein the order corresponds to the highest derivative of the differential equation, while the degree corresponds to the exponent of the highest derivative. And lastly, the properties or the linearity of a differential equation, so which depends solely on the dependent variable. So to make it linear, the power of the derivatives of the dependent variable should be equal to 1. And then there should be no transcendental functions involving the dependent variable y. And lastly, there should be no product of the dependent variable y and its derivatives. So if there is, okay, so that would be considered as a nonlinear ordinary differential equation. So let's proceed with some of the examples. And then let's try to answer some of them. So I'll have example number 1. So classify the following differential equations as ordinary differential equations or partial differential equations. So again, from here, we are only looking at the number of independent variables. So if there is one independent variable that is considered as ordinary differential equations, and if there are two or more independent variables, then that is considered as a partial differential equations. So let's proceed with the first one. So we have the 1 minus y prime plus y is equals to e raised to x. So remember that y prime is the same as dy over dx. And since there is no other derivative that is involved on the example 1a, so wherein it only involves y prime, so therefore we have only one dependent variable y and one independent variable y. So therefore the classification of the differential equation is ordinary differential equation. The second one, okay. So let's say we have the second derivative of y with respect to r, and then the derivative of y with respect to u, plus y is equals to cosine r plus u. And then from here, so it is obvious that our dependent variable, okay, our dependent variable is y. However, our independent variable, so we have r and u. So r and u. So therefore, this is considered as partial differential equations. And lastly, so let's have the third one. So it says here that it is an ordinary differential equations. So we have a dependent variable. So our dependent variable is r, and then our independent variable, that is equivalent to t. Since there's only one independent variable, therefore that is considered as ordinary differential equation. But sir, what is k? Okay, so is k a variable? So since k does not involve any derivative, okay, so even though that is a letter, so k here is considered as a constant. So it is k there is not variable. It's not dependent variable. It's not independent variable, but rather it is a constant. So the dependent and independent variable can only be seen, okay, so as long as those variables involves derivatives. So if it is not, that is considered as a constant. So therefore, this particular example is considered as ordinary differential equation. So let's proceed with our second set of examples. In this case, so we will be classifying the following differential equations according to order and according to degree. On the first equation, so we are given the second derivative of y with respect to x plus sine y is equal to 0. And from here, there's only one derivative, okay? So which is the second derivative. So therefore, making the order of the differential equation to be equivalent to the second derivative. And then the power of the second derivative is equal to 1. So therefore, its degree is equal to 1. So second derivative of y with respect to x plus sine y is a second order differential equation, and it is a first degree differential equation. So let's have Example number or second example. So we have the second derivative of y with respect to r plus the first derivative of y with respect to r cubed plus y is equals to cosine r plus u. So there are two derivatives involved, the second derivative and the first derivative. So therefore, the order of the differential equation would be the higher derivative, and or sorry this and then the degree so corresponds to the exponent of the highest derivative. So we will not be looking at the third there. So therefore, this particular example or this particular equation is a second order differential equation and a first degree differential equation. So lastly, so let's have the second derivative of y with respect to x is equal to the square root of 1 plus dy over dx raised to 3. So in a differential equation, to properly classify whether a differential equation or whatever would be the order and degree of the differential equation, the differential equation should be from any rational exponents. In this case, so there is a square root that is involved. So therefore, so what we will be doing here is we're going to raise the entire equation by 2. So giving us the second derivative of y, so with respect to x, raised to 2, and then that would be equal to 1 plus dy over dx raised to 3. And then from there, we'll be able to see that the higher derivative would be the second derivative over the first derivative. So therefore, the order, okay, would be a second order. And then, just look at the exponent of the highest derivative, so which is 2. So therefore, the degree would be 2. And thus, giving us that the equation is a second order and a second degree differential equation. So that's it on determining the order and the degree of the differential equation. So let's proceed with the last set of examples that we have. In this case, so we will be classifying so whether the following differential equations are either a linear or a nonlinear ordinary differential equation. So in determining the linearity of a differential equation, so let's try to have a checklist. So the first on the checklist so would be whether the given differential equation so involves a power for its derivative which is more than 1. Okay, so the first criterion, how many derivatives that we have that we can see here? So it's only 1. Okay, so it's only 1. And then the power of the first derivative. Okay, so the power of these. Okay. So the power of this given derivative is equal to 1. So therefore, it satisfies our first criterion. Okay? So the power of the derivatives is 1. Anything other than that, that is already classified as an ordinary, or that is already classified as a nonlinear differential equations. How about our second criterion? Our second criterion states that no transcendental functions involving our dependent variable. So remember that y prime is equivalent to dy over dx. So therefore, our dependent variable is y. And there should be no transcendental functions involving y. Okay, but in this case, there is, because we have e raised to y. Exponential function is a transcendental function, and then it involves the dependent variable for our transcendental function. So therefore, it already fails on our second criterion. So making our first example to be a nonlinear differential equation. So that is because of our second criterion. It fails on the second criterion. Although on the third criterion, so there should be no product of y and its derivative. So since the first derivative is not multiplied to any other dependent variable, so therefore that would still be, or it satisfies that given criterion. So next, let's have the second one. Okay, so for our second example, so we have the fourth derivative. There is a fourth derivative, however, okay, there is a fourth derivative for our differential equation. Okay, so fourth derivative for our differential equations. However, it contains a variable with a power more than 1. So aside from although the exponent of the derivative, okay, the exponent of the derivative is only 1. However, we have a dependent variable y, and then it is raised to 2. Okay, so therefore, on our first criterion, it already fails. So making it as a nonlinear differential equation. Although for our second criterion, there is no transcendental functions, so therefore that would be okay. And then the third one, so there is no product of the dependent variable and that of our derivative, so that would still be fine. But it already fails on our first criterion, wherein the power of our derivative should be 1 together with the dependent variable should be 1 as well. So making it a nonlinear differential equation. How about for the third differential equation? So we have x to the fifth y triple prime minus x cubed y double prime plus 6y prime is equals to 0. So first criterion, so the power of this is 1, second derivative is 1, first derivative is 1. And then there is no dependent variable other than the derivative, so therefore it is okay with our first criterion. However, for the second criterion, transcendental functions, there's no transcendental functions involved on the differential equation, that would be okay. And lastly, there should be no product of the dependent variable and the derivatives. There is a product on the derivatives and a variable. However, x to the fifth, x cubed, x is considered as independent variable. So therefore, even though that x is a variable and then it is multiplied with the derivative, that is still fine because x is not a dependent variable. It is independent variable. So thus, it satisfies all the criterion, and that makes it as a linear differential equation. And then lastly, so can we classify this one as a linear or a nonlinear differential equation? So we have here, so let's classify. So one, two, three. First thing first, the derivatives. So the power of this is 1, the power of dy over dr is 1. And then the power of our dependent variable y is 1 as well. So therefore, it satisfies our first criterion. Second criterion, no transcendental functions. We have transcendental function which is cosine. But let's take a look. How about r and u? So what's the classification of r? So r is independent, while u is not a variable. So that is considered as a constant. So that means even though that cosine is a transcendental function, but it involves a constant and an independent variable. So therefore, that would be okay. And lastly, so there should be no product of dependent variable. So y is not multiplied to dy over dr, nor it was multiplied to d or the second derivative of y with respect to r. So therefore, it satisfies our third criterion. So making it as a linear differential equation. Okay, so that is the last set of our examples. So hopefully you understand. Okay, so our topic for this introduction to differential equations. So to sum it up again, there are different classifications of differential equations. So again, differential equation is just an equation of derivatives. So it could be classified according to its type, according to its order, degree, and linearity. So when we are talking about the degree, or when we are talking about the type of the differential equation, an ordinary differential equation so involves dependent variable and only a single independent variable, while the partial differential equation so involves partial derivatives but it also involves two or more independent variables. So that is how we classify the differential equation as ordinary differential equation or partial differential equations. For the order of the differential equation is always the highest derivative on the given equation, while the degree of the differential equation is just simply the exponent of the highest degree. So given that the equation is free from rational exponents, or it is free from radical signs. And lastly, the linearity of the differential equation depends on three criterion. It must satisfy all three criterion before it could be classified as linear differential equation. Any violation among the three criterion, that is automatically it becomes a nonlinear differential equation. So again, the three classification would be the derivative or the exponent of the derivatives as well as the dependent variable should only be one. The second criterion, no transcendental functions involving independent variables. So all the transcendental functions should only involve independent variables. So if not, that is considered as a nonlinear differential equation. And lastly, there should be no product involving the derivatives as well as that of the dependent variable. So those are all the uh, parameters, okay, or the classifications of differential equation. Thank you.